and I'm really excited that Gabo is here because he's done really cool lot of cool stuff around graph querying, a complex model and large models, and he will talk today about incremental graph querying. So let's welcome him, and we're up for the recording.
So, welcome everyone. My name is Gábor Szárnyas. I'm a PhD student at the Hungarian Budapest University of Technology and Economics, and I also worked as a visiting researcher in Canada at McGill University. My talk today will be about incremental graph queries with openCypher. So, let's dissect this title and first talk about incremental graph queries. Why would we want to use incremental graph queries? Well, let's imagine a simple railway network where there are railway segments and trains are traveling all along the railway network. Obviously, this is a safety critical system, so if there is some malfunction or a design error in the system, serious damage in property can occur or lives can be threatened. So it's absolutely important that we get this right and we closely monitor this system 24 hours a day, 24 hours a day and 7 days a week. So we define constraints that must be kept during the running of the system. For example, if we have trains too close to each other, we might issue a dangerous proximity and say that one of the trains must stop as they might crash. Also, in this system, there might be switches that navigate the trains, and there is an interesting constraint in railway networks is that if the switch is set to a diverging position, then the train cannot travel from the other direction because it might damage the switch. This is called trailing the switch. This is also something that we want to avoid because it damages valuable hardware. Okay, so how do we model this as a graph? It's not that difficult. We just say that each segment will be a node in the graph, the trains will be nodes in the graph, and then the switch will be a node in the graph, storing its position as divergent. So we add some edges. Now we have the trains are on the segments are stored pretty much as a linked list, and then we have the switch with the appropriate directions. So if you want to do the proximity detection constraint, we say that if the trains are on adjacent segments or they have less than 2 segments between them, then we might issue a warning. So as a graph pattern, this might look like this. We have a train, a segment, and then there is a single segment or 2 segments between the segments that the trains are on. This is pretty much a simple Cypher query. You can just take the graph pattern and describe it in the usual Cypher syntax. If you run it in Neo4j, it generates a query plan like this, and it executes and returns the values. So for trailing the switch, we have another constraint. It looks like this. We have a train which is on a segment which comes straight from a switch, but the switch is set to a diverging position. So this is something that we would like to avoid, and then we would like to warn the users. Neo4j is also capable of running this pretty efficiently. However, in such a system, we need to evaluate such queries continuously, so we need to run these queries over and over and over again. And this is basically the idea of incremental graph queries. We register a set of so-called standing queries in the system, and we continuously evaluate these queries upon each change in the graph. There is a quite simple algorithm which is called the RETE algorithm. It actually comes from 1974 and was originally designed for rule-based expert systems. The main idea of the RETE algorithm is that it indexes the graph and caches the interim results in a network. RETE actually means net in Latin, so this defines a propagation network for the query, and it stores the results so that it can only maintain the results upon changes. So how does this look like in practice? For the second constraint, trailing the switch, we have the graph pattern, and this is our RETE network. As you can see, you have your usual relational algebraic operators like joins, selections, and projections. So if we take the graph, then first what we do is index the graph for the appropriate edges. So first we gather the on edges to the indexer on the left. Then we gather the straight edges to the indexer on the right. And now we start to calculate the results for the graph pattern. So what we do is join the nodes that are connected. So we have the train on the segment and next to a switch. We do a filtering operation which enforces that the switch is in a diverging position. And then in the end, we project, and we only need the number of the train and the switch that is next to the segment. So what's the advantage of this approach? Well, if the train moves slightly, for example, it moves from E to segment D, then we only have to recalculate a small portion of the network. In this case, we propagate the change through the on indexer, and then there are no more matches in the join operator, so we have no more issues because the trailing the switch constraint is now not violated. So to summarize, usually graph databases and relational databases use batch queries, which are more request driven. There is a client, and the client issues a query, the database calculates the query results, and it returns the results. The results are obtained on demand, so the client has to specifically ask the database for the query results. In contrast, incremental queries are more event-driven, so the client registers a set of queries in advance, and then for each change in the graph, the results are maintained, and this is a continuous loop. The query results are always available for the client. So in the past, there have been many implementations for incremental query engines. One of the most well-known is the CLIPS rule-based expert systems, which was developed at NASA. There is Drew's Reta-based engine, which is part of the JBoss stack and is developed by Red Hat. And our university developed the Viatra query framework, which works on the Eclipse modeling framework and is quite widely used in the modeling community. We actually have a spin-off company called Inquire Labs, which continuously develops Viatra and provides support. So these are the academic and industrial tools, and we have some very prototypical tools like Instance, which works on RDF and is developed by Aalto University. We have a Scala-based solution called i3QL, developed by the Technische University at Darmstadt. And we have InquiryD, which was my early PhD project in my university. So what we don't have is a property graph-based implementation. So as far as we know, there are no incremental query engines for property graphs yet. But this is about to change. So first, we need a good query language and a good ecosystem that we can integrate with. So what is openCypher? As you probably know, the Cypher query language aims to be the sequel for graph databases. So this means that Neo technology tries to provide a standard for its query language. This comes with the obvious advantages that users will not be afraid of getting logged in with a specific vendor. Instead, they can rely on the grammar specification and the reference implementation, and also the openCypher kit provides a so-called technology compatibility kit, which allows the developers to test their own openCypher compliant engines if they really comply with the rules of the openCypher language. So openCypher actually defines a smaller subset of the Cypher query language, but it still allows you to do many interesting things. You can do almost all of the pattern matching stuff that you can do in a normal Neo4j Cypher. You can do your filtering operations. There are collections like lists and maps. There are operators for data manipulation, and also more advanced constructs like variable length path. So some features are excluded from the standard. These are called the legacy constructs. These are mostly implementation-specific stuff like load CSV, index, constraints. There are regular expressions, which are notoriously difficult to get right between different programming languages. Some of the more sophisticated list functions, for example, reduce, are removed because these are very powerful and you can almost program with reduce in your queries. And there are a lot of predicate functions removed, functions that calculate the shortest path, case expressions, and IDs. And interestingly, and somewhat accidentally, some of the legacy constructs are also very difficult to handle internally. So in our prototype implementation, we do not focus on the legacy constructs, but try to implement a meaningful set of the standard constructs in openCypher. So in order to implement our incremental query engine, we first mapped the openCypher query language to relational algebra. This is quite a long mapping. We had to define some custom relational algebraic operators, and we gathered our findings to a technical report, and we published this technical report online. It's built continuously on every change in our system. So basically, what you see in the technical report is the latest version as compiled by our parser and our query engine. So we gathered a lot of queries from Neo4j use cases, for example, tutorials, our use cases, blogs, GitHub, and we translated these queries to standard batch search plans defined by relational algebra, and then we translated these search plans to incremental search plans, also defined in relational algebra. Some of the findings that we have is that some constructs, even in standard openCypher, are very difficult to get right incrementally, especially lists, because you have to treat the lists with the appropriate granularity, and that's not easy if you have lists that are nested into each other, and then you can unwind these lists, and then you can collect these lists back together. This is something that's not easy to get right. Also, standard Rete implementations use set semantics. In contrast, openCypher uses back semantics, and you can also order your results and select the top n or skip some results in the result set. And as I mentioned, shortest path and all shortest path are quite difficult to get right incrementally. There are some papers in the topic, so in theory it can be done, but you have quite complex algorithms that do not always perform well in practice. So these challenging features in Cypher are those that are not traditionally handled by Rete implementations. We are looking into implementing the standard construct and see what we can do about the legacy construct. So by now we have a tool which we call InGraph, an incremental in-memory graph query engine. Basically, InGraph works in a client-server architecture. The client registers a set of queries, and then it continuously updates the graph through another queries. And the client can either retrieve the query results, or it can subscribe and get change notifications for new results in the query set. So how does InGraph look internally? Well, it pretty much looks like any other graph database or graph query engine. It takes the query specification and builds a query syntax tree. Now, as I mentioned, the openCypher initiative provides the grammar for parsing the queries, but it provides an ANTLR-based grammar, and while experimenting, we found that the ANTLR grammar is a bit too low level. So we kept looking, and eventually found something called the Sliza software architecture workbench, which implemented the openCypher language in Xtext. Now, Xtext is an Eclipse project based on top of ANTLR, and it provides a really nice and high-level way for accessing the parse tree that's built from the query specification. So we use Sliza's Xtext language, and then we build the relational algebra model through a code implemented in Xtend, which is, as you have probably guessed, a technology that's built on top of Xtext. So this is a technology that allows us to very efficiently implement the algebra builder, and we build this on top of Eclipse models. So the parser takes this input, and then it builds a simple search plan, which is basically a relational algebraic expression. So now what we have to do is somehow transform this to a Rete network, which allows incremental computation, and deploy it. So first, we transform it and add some optimizations. Interestingly, for the transformation and the optimization, we use Vietra, which on its own is an incremental graph query engine. So we use an incremental graph query engine to drive another incremental graph query engine. In the end, we get a bit more complex network, which is the Reta network, and we use our query deployer, which uses asynchronous technologies and functional programming like Scala and the Akka toolkit. So why do we use these technologies? Well, if we revisit our slide on the trailing the switch constraint, we find that the Reta nodes that perform the computation can be thought as actors in the actor programming paradigm. And actually, this model lends itself very well to the actor programming paradigm, because you can think of the propagation of the tuples in the network as asynchronous messages, and this works pretty well in practice. We did a lot of experiment with parallel implementations and distributed implementations, and they scale quite well, but they are pretty difficult to set up. So currently, InGraph is a single node tool, but it, in theory, can work on multiple computers as well. So one of the challenges that was pretty difficult is to get properties right, because traditionally Reta uses simple tuples. You have primitives like IDs, strings, booleans, floats, and so on. In contrast, here we have something like t.number, which is a primitive, and then we have SW, which is a switch, which is a whole node in the graph. So what we do is we build a Reta network first, and then run a three-step inferencing. First, we say that we infer the schema of the operators. So we start with the schema of the indexers and then build up the tree. Second, we start traversing down the tree and gather something called the extra attributes that will be required for computation or for returning the query results. So we gather the numbers, and then we see that we need, for the filtering, the position of the switch. So we also note that we need the number and the switch position. We propagate this to the bottom. We notice that we have to propagate the number to the right, and then the number to the left, and then the position to the right, so like so. And then finally, we traverse the tree from the bottom to the top and infer the schemas again. And then we have the schemas, and this comes with the advantage that we don't have to unnecessarily propagate the whole nodes and the whole relationships up this tree, and this saves a lot of memory in practice. So let's revisit the relay model. As I said, in practice, we want all of these queries to be evaluated 24 hours a day, 7 days a week. So continuously, and all queries must be evaluated. Fortunately, this is quite easy with the Reta network, because we can use the Reta network to check multiple queries. So as you've noticed, on the right, we have the trailing the switch constraint, and on the left, we have a new constraint which takes care of close proximity. So it checks if the trains are in too close proximity to each other. And as you can notice, we have a feature called node reuse, which means that if we have a node that is used by multiple parts of the Reta network, then it can be reused, and this saves a lot of memory if you have a lot of constraints. So the figure also shows that the Reta network is basically a DAG, a directed acyclic graph, and that allows it to reach a fixed point pretty quickly upon evaluation. So how does this Reta network work in practice? We have another animated slide for that. Basically, we have a bit more indexers, and then we evaluate the projections. We calculate the join. We now find that train 1 and 2 are too close together, so we issue a warning to the user that 1 and 2 are too close together. 1 is on A and 2 is on D. So some time passes, and our train moves from segment D to segment E. And this shows the advantage of the Reta network, because now we only have to propagate the changes to the indexer. We change the 2D tuple to 2E. And then we have no results on the dangerous proximity results, but we will have some results in trailing the switch, because this train is about to hit the switch that's set to a divergent position. And obviously, as I said, this is a maneuver that's illegal in railway systems. So I would like to highlight some use cases. We have a model validation framework called the train benchmark, which is also built around a railway network. But instead of doing runtime checks, we do checks during the design of it. We have a static analysis framework for JavaScript source code that I will talk about in a minute. And also, I think that incremental queries can be beneficial for all use cases where you have standing queries on a large and continuously changing graph. So if you have a fraud graph and you would like to detect fraudulent links or users that are doing fraudulent behavior, then incremental graph queries can be very useful. Also, if you have a huge IT infrastructure, that can also be modeled as a graph. And obviously, it's changing very quickly, and you would like to have a lot of warnings in case something goes wrong. So the first use case, the train benchmark railway validation, is basically a benchmark paper with the implementation available on GitHub. We implemented a set of scalable generators. We can generate graphs in the Eclipse modeling framework, property graphs, the semantic webs, RDF format, and SQL for relational databases. And the benchmark defines a set of validation queries that must be enforced during the design of the railway network. We implemented this for more than a dozen tools and implemented automated visualization and reporting stuff. So if you have a graph query engine that you would like to use on large and continuously changing graphs, it's worth giving a try to the train benchmark system. Another use case is the static analysis of JavaScript applications. This is a very simple example. You have a division by 0 in your source code, and you can detect this by building a syntax tree and doing pattern matching on the syntax tree. So basically, this Cypher query allows you to catch division by zeros in your source code. Now, obviously, this is a very simple example. So in practice, you have much more power when you have your whole repository represented as a graph. You can do stuff like that code detection in your whole repository. You can do type inferencing if you don't use TypeScript or any other languages that allow static typing for JavaScript. And then you can use these for generating unit tests for your code. So until now, we formalized most of the standard openCypher language and gathered our findings to a technical report and implemented a research prototype for the railway model validation queries. In this quarter, we plan to use the TCK tests, which are provided with openCypher. This will allow us to increase the coverage of our mapping and probably will also reveal a lot of bugs in our parser and in our query engine. And once we are done with that, we will implement a more sophisticated optimizer using technologies from the Apache stack, probably Spark Catalyst or the Calcite system. And we plan to publish our benchmark results in a top-tier academic conference. So to summarize, I presented some open source projects, the InGraph project, which allows you to evaluate incremental graph queries in openCypher. There is a train benchmark system that allows you to benchmark such queries on realistic large data sets. And then we also have a very interesting demonstrator called the Modes 3 project, which is the model-based demonstrator for smart and safe systems. This is a demonstrator that revolves around the idea of a cyber-physical system, and it uses a model railway and a lot of real-time computation to make sure that the model railway works safely. These are all available on GitHub with continuous build and licensed under the Eclipse public license. Thank you for your attention.
So we have 5 minutes for questions. Any questions from the movie?
Okay, you start first.
Yeah, thank you for wondering, so the query plan that you initially produce, does it change when the graph changes? So for example, those query plans are often built using cost-based optimizers, for example. And if, for example, during the loads, so the graph changes, the statistics change, does this query plan adapt to this?
Yeah, so the question was that do we use a cost-based optimizer, or can we change the query plan upon execution, or do we use some statistics? And this is a very good question. And the RETA algorithm has some very good properties with this respect, because once you have your query, you can determine which graph nodes and graph edges you will need for computation, and you can build only the lower level. You can build the indexers from your current model, and you can use these as an input for your cost-based optimizer. And as I mentioned, we plan to use the Spark Catalyst framework. I started implementing a cost-based optimizer on my own, and it turned out to be very, very extremely difficult. So we thought it might be a good idea to use Sparks or the Calcite frameworks optimizer, because obviously these are more sophisticated. And regarding the dynamic reconfiguration, that's something that you can theoretically do with the RETA algorithm. We had some experiment with that. We have a system that does a design space exploration, which is basically a search, but it allows you to dynamically reconfigure a system. So design space exploration will look for a better solution, and then it will also give you the steps that you need to take to transform your system to another representation. This is something that is very interesting from an academic perspective, but it's super difficult to get right in a real system. So this is something that works just in theory yet. Okay, next one.
So my question, this event propagation graph that I see on the screen right now, it looks to me exactly like an event propagation graph in a reactive program. Is that true?
Yes, there is a lot of truth to it. And basically, this is very useful if you want to maintain incremental views. So if you have, as I said at the beginning, the main difference between the so-called batch and incremental queries is that one is more pull-based and the other one is push-based. This is a very nice fit for reactive applications, I think.
And so this RETA algorithm is implemented as actors, each propagating messages?
Yes, so basically you have actors, and obviously, unfortunately, the actor model allows you to store mutable state in the actor. So this state is mutable, but between the actors, all the messages are immutable. So you do immutable message passing, and this allows you to run the calculation in a distributed way and in parallel. Okay?
You did some sort of pre-compiling your model. So assuming that the railway system is static.
Yeah.
What would happen if this network of rails would not be static? Would you still be able to pre-compile something, or would this simply not be possible?
So the question is that if we took advantage that the railway network is static and only the trains move around the railway network, so basically this didn't really take advantage of that. You can quite easily do it with a whole pretty much fully dynamic model, but there are a lot of use cases that look like the following. You have a big set of static data. You have a smart city, and you have the buildings and the infrastructure, and they don't really move anywhere. And then you have the dynamic stuff like vehicles, like weather, people moving around. RETA is, I think, quite a good fit for this, but this is not a requirement. This is just something that works really well with this algorithm.
I have a question. One thing that I could imagine it's quite difficult to do is aggregation. So if your query contains aggregations, because you have to kind of be able to track back where the aggregations originate from, and if they're lossy, then it might be a difficult thing.
Yeah, actually, this is listed in the challenges in the openCypher stuff, somewhere between the lines. So basically aggregation, it is collection and lists. And basically, even if you want to maintain something like a minimum or a maximum incrementally, you have to store all of the possible candidates, so all of the interim results, and then you can serve this. Obviously, you can store it in a heap or in any efficient data structure, but aggregations are quite difficult and are usually not supported by Reta engines.
Okay, cool. So time's up. If you have more questions for Gabo, then please ask him later.